Okay, today's video lesson is going to be on hybridization of atomic orbitals. Just a little disclaimer here. This video lesson, I'm going to go through the explanation of the hybridized orbitals. AP test is not going to ask you to explain the origins of the hybridization. All they want you to be able to do is predict what type of hybridization at the end. Alright, so what is hybridization of orbitals? Well, we talked about atomic orbitals, and that would be the s orbital has that spherical shape to it, right? You have that spherical shaped s orbital. You have the p-shaped orbitals, and you've got three of the lobes for that one. You got the one that goes like this and like this. One goes up and one goes down, and the other one comes out and goes into the back. Anyway, so those are the atomic orbitals, and that was for atoms. But when we come and start looking at molecules, things like CH4, okay? Whoops, it was a weird 4. Okay, so we have things like methane, okay? We need to explain the structure of this methane. Now, what we know about methane is that it has 4 binding areas around that central carbon, and each of those bonding areas are pretty close to being identical to each other. Okay, each bond length is the same. Each bond energy is about the same. So if we're going to account for these 4 bonds, they all have to be exactly the same. But there's a problem, because if we have carbon, carbon has its 2s orbitals filled. Okay, these are the atomic orbitals that we're talking about, and its 2p orbitals are filled. Well, not filled, but one's half filled, and the other one's half filled, and the other one's empty. So I guess they're not even close to being filled. But anyway, you get the idea. Alright, so we got the electrons here. Now, if the hydrogens come in, hydrogen has a configuration of just 1s, right? You got a single electron in the 1s orbital. Alright, so the electrons should, for each of those hydrogens, kind of go in here and fill in the space here. Okay, but there's a problem, because even if we get one hydrogen here, another hydrogen here, there's an empty orbital, and the problem is that this isn't going to work as it's written, because we need 4 bonding areas that are exactly the same. So something has to happen to carbon's orbitals, and that's what we're talking about with hybridization. What's going to happen is these orbitals that we talk about as atomic orbitals are going to change to what are known as molecular orbitals. Okay, so the atomic orbital is going to change into a molecular orbital. Okay, now you don't have to really, like I said, get into the origins and explanations, but I'm just going to kind of show it to you on this next slide here, or at least try to give you an idea of it. Okay, so let's take a look at what's going on. So here's the s in the p the s and the p orbitals for carbon. So as I said, for carbon, this would be the 1s. And the, sorry, not the 1s, but that would be the 2s and the 2p. Okay, so we'd have 1, 2, 1, 2 for carbon. Alright, now what happens is, again, don't worry too much about explaining the origins of all this, but what happens is the electron here gets promoted up to this higher energy level. And this energy, remember, electrons are going to need energy to do this. In order to get this electron from a 2s to a 2p, a higher energy, is going to require energy. Where does this energy come from? It comes from the chemical bond itself. So when CH4, methane, is formed, energy is going to be used to make this molecule. Well, what it does is it causes an electron to be promoted up, and you end up with this new configuration, or at least the configuration will now look like this. You have 1 electron in the 2s, and you now have 3 electrons in 1, 2, 3. Okay, so what's going to happen now, we have an electron in each of these orbitals, and they're different though. Here's an s and these are p's, and those are different orbitals. So something is going to happen, and what happens is this hybridization. And what that means is that these orbitals here are all going to come together to create a new set of orbitals. Okay, and those orbitals are now called Sp3 orbitals. So we have 1, 2, I probably should have drew another box. We have now what's called a 2sp3 hybrid orbitals. What's happening is these s's and these p's are morphing together to create new orbitals. I know this is very abstract, crazy concepts, but again, this is one theory that explains possibly what's going on in the orbitals. Things are getting very, very abstract at this point. So now these 4 electrons are in a new type of orbital called the hybrid orbital. Okay? Okay, and a hybrid orbital is one that has the S's and the P's morphed together. Now I have 4, and notice that all 4 are exactly the same. They're all now Sp3s. They're not S's, they're not P's, but now they're all Sp3. And I get one in this direction, one coming out at us, one going to the right, and one going up. So we now can put these all together, and now we can make sense out of the carbon. So what carbon does is it has these Sp orbitals or lobes that are kind of coming out and going and doing this kind of thing. Okay, so you can kind of envision this. And what happens is the hydrogens, there's still going to be an S. Nothing happens really with the hydrogen. So the hydrogen bonds here, another hydrogen will bond back here, another hydrogen will bond over here. Because of these S's are what the hydrogens are going to look like, there's no morphing. Now this doesn't happen with everything. Okay, so anyway, maybe I'll explain in just a second what it doesn't happen with everything. This would be my Sp3 hybrid orbitals. Okay, and there's 4 of them for carbon. So now we're going to look at what are called Sp hybridized orbitals. So these are just Sp hybrid orbitals. Okay, so what does this mean? What we're doing here is we're going to take the beryllium atom, and we're going to have the 2s2 is filled. Okay, if you draw the configuration in the orbital diagrams, this is what you're going to get, and there's an empty box in the p. Now, the sp comes together and morphs into what's called an sp orbital, leaving behind the 2 p's. Notice these 2 p's over here don't get into the mix. They actually stay just as they were before. And when we have my 2s, 2p comes together, we get this sp thing, and this is another one, and these join together. So we have the 2s, 2p come together, they make a sp and an sp. Then they join together and they create these new lobes known as an sp hybridized orbital system. And this explains what's going on in beryllium. If you look at this shadowy image of beryllium, there's an electron here and an electron here, right? That's what this is showing right here. Okay. Now chlorine comes along, and chlorine has a lone pair of electrons, or a single electron is going to bond and overlap here, and another bond is going to form over here. And you can see that this explains that linear structure for that beryllium dichloride. So this would be BeCl2. Notice it's a deficient in octet, and we get a linear structure to this. Okay, you get a linear molecule. Do that sp hybridized orbital on the beryllium. Notice the p's are still there. The 2 p's are still available for the beryllium, and therefore if it's going to react, if another element comes by like water that has a lone pair of electrons on it, well, beryllium will definitely bond with that and fill those orbitals up. Okay? Alright, so that's your sp hybridized orbital. You're just taking an sp and putting it together. Okay? The rules still apply. Each one of these can hold 2 electrons at most, right? 2 electrons at most, and therefore 4 electrons, and that's why beryllium does what it does. Okay, so let's look at the sp2. Okay, so this would be sp2 hybrid orbitals, and this is where we're taking an s and combining it with 2 p's. Again, s and 2 p's. A single p will still be left over. 1, 2, 3, and this is going to give us our trigonal planar structure. This would be for boron trifluoride. And boron trifluoride has sp2 hybridized orbitals, and it leaves behind that single 2p orbital left over. And then fluorine can bond on either side of it and create the structure. Alright, so that accounts for, let's see, I got a chart here that kind of summarizes these for you. So if we look here, we got our 2 electron pairs, that would be sp. And that would be our linear shape. Okay. Now for our trigonal planar structure, we have sp2 hybridization. So anything with this trigonal planar structure is going to have sp2 hybridized orbitals. Okay. Anything with a tetrahedral structure is going to be sp3 hybridized orbitals, because it's going to have 1, 2, 3, 4 areas around it. Okay, and then we get into these expanded. So this would get, if you go back to that chart that I showed you before, where we were looking at the molecular geometries, this would be my deficient octets up here, right? Or my double bond, triple bonds, which would give me that linear shape, or it can give me that trigonal planar. Okay, something like HCO4 carbon, actually H2CO. That would give carbon with a double bond and a single bond on the hydrogens. Okay, that would have a trigonal planar structure. The carbon here would have Sp3 hybridization, and I'll talk about double bonds and single bonds in the next video. Okay, anyway, so we've got 5 down here. This would be our expanded octet. What does an expanded octet require in order to expand? It requires at D sublevel, and that's in its configuration. All right, I'm just going to show you one more where that I can show you the origins of the Trigonal Bi-Pyramidal. Okay, because it has to have 5 areas in it, so SPD. Okay, so to take a look at the Sp3 dehybridization, let's take a look at phosphorus pentachloride. Okay, so for phosphorus pentachloride, we're going to look at the structure for phosphorus. Phosphorus has 5 valence electrons, so we're going to go ahead and put these in its second energy level. So second energy level, 1, 2, 2p, and we just do 1, 2, 3. Now to get this phosphorus pentachloride to work, what we need to do is we need to get a trigonal bipyramidal structure. Okay, so we need a trigonal bipyramidal, something that has 5 bonding areas that are the same. Well, the problem is, this should be a 3 by the way, not a 2, because it has to be in a third energy level. So we have the 3D. 1, 2, 3, 4. Okay, so what happens is this electron promotes up to here, and we get a hybridization of all of these orbitals, including one of the Ds. So what phosphorus does is it has a 3sp3d1, and that is going to give us 5 orbitals. So you get 1, 2, 3, 4. Okay, 1 electron, 1 electron, 1 electron, 1 electron, 1 electron, and then you have the 3d still remaining with the left in it with those 4 empty boxes. Okay, so there would be your Sp3 dehybridization. Okay, and I'm sure you can envision what would happen with an Sp3d2. You would just encompass one more D in there, and you would end up with an Sp3d hybridization. So I'll start answering all your questions. I know I get a lot on this thing because it's kind of confusing, but I'll see you in class. Thanks.